Hello. So, hi, Sudarshan. Good
Hello, sir.
evening.
Good evening,
Yeah.
sir.
So, welcome to week number 6 of this course on advanced power electronics and control. So, I will just start now. Just a second. Yeah. So, is my screen visible, Sudarshan? Can you just confirm?
Yes, sir. It's visible.
Yeah. Thank you. Okay. So, in this week, predominantly, you would have read about DC to AC converters, right? So in the last week, we saw problems on DC-DC converters, right? We covered mostly all kinds of problems on basic non-isolated converter topologies, that is the buck boost and the buck boost. And we also saw a problem on Chu converter, right? And I think we covered problems on DCM as well, right? That is just critical conduction mode as well, in addition to the normal continuous conduction mode, right? So in this week, we'll be seeing problems on inverters predominantly, mostly on voltage source inverters, and a few problems on some PWM techniques, right? But anyway, theoretically, you would have studied about voltage source inverters. Then you have the classifications in them, that is, they can be single phase or three phase. You would also have studied about the harmonic content and the harmonic analysis, right? So for single phase and three phase, then you came to current source inverters, wherein you did the pretty much the same thing, right? And then you also went through some PWM techniques, namely the uniform PWM technique or the square wave PWM technique. Then you were introduced to sinusoidal PWM or the SPWM technique, right? And finally, towards the end of this week, you also went through space vector PWM, right? Other than that, you also went through the multi-level inverters and, of course, the Z-source inverter, right? Just some theoretical aspects about them, correct? So today we'll be having the problem-solving session, right? And as usual, I have a set of a few problems. We will first solve them. Once we are comfortable with that, we will go ahead with some more if time permits. Okay, and at any point of time, if you have any doubts, you are welcome to stop me and ask me in the middle as well. Just a second. Okay, so a single phase half bridge inverter is feeding power into a load of resistance 10 ohms. DC input to the inverter is 400 volts. Then determine the power delivered to the load. Okay, it's a classical single phase half bridge inverter problem. So these are problems that you can expect when you actually give your problem exam, right? Okay. So R is given and the VDC is given, right? So they are just asking you to find out the power, correct? So as we did with DC-DC converters, it is better if you can actually draw the circuit diagram. Okay, just the converter alone. If at all you don't remember the formula, if you remember the formula, well and good, you can just go ahead. Okay, but anyway. So this is the topology for a single phase half bridge inverter, right? So you have two switches S1 and S2, and to the midpoint you have the load connected, and it is kind of connected to the midpoint of your DC bus, right? So what I mean by DC bus, midpoint of DC bus is the point O. At the point O, you get a voltage of VDC by 2 and VDC by 2 on either sides, right? So you have the plus terminal, then the O terminal, and then the negative terminal. Okay, so that's the idea. And when S1 is turned on, you know that the current flows from A to O, correct? So VAO is the polarity of the voltage. So VTC by 2 gets applied across VAO, right? And during the other half, that is the complementary cycle, right? So S2 gets turned on and S1 is turned off, right? So S2 is turned on means obviously you understand that VAO is going to be negative, correct? Because you can understand that this particular point is going to be plus VDC by 2. And this is going to be V by another VDC by 2. Okay. So when S1 is turned on and S2 is turned on, you can understand what voltage is actually going to get applied. Correct? Okay. So since they have also mentioned that it's a resistive load, right? So the current is exactly going to follow your voltage. Okay. So that is why these current waveform is also going to be something like a square wave, right? So with this available information, you know what is VA naught and you know what is I naught, right? So from this, you can obviously determine the power. Power is simply multiplication of voltage and current, correct? Okay, sorry for that. Okay. So what is VA naught? VA naught is VDC by 2, obviously, right? Because as I told earlier, the point O, right? The point O is connected to the midpoint of your DC bus. Okay. So at one particular interval, when one switch is turned on, the voltage across your the load is going to be either plus VDC by 2 or minus VDC by 2. It's only bipolar, right? Only it can only have two values. Okay. So that is why VA naught is going to be VDC by 2, which is 400 by 2, which is 200 volts. Okay. Then your IA naught, since it's a simple R load, IA naught is simply VA naught by R. Okay. So that is 200 by 10 and it's 20 amperes. Therefore, what is your peak? P is simply V into I, right? So 200 into 20, that's 4 kilowatts. Okay. So the answer is D, 4000 watts. Okay. So I hope you got this problem. It's a very pretty simple problem, right? So just find out what is VA naught, find out what is IA naught, and just multiply them, you get the answer. Okay. Okay. Find the conduction time of the diodes if the SCRs are fired at 0 and T by 2 respectively in a single phase half bridge inverter with R load. Same question, same topology. Just you need to find the conduction time of the diodes. Okay. So first try to understand what do they mean by diodes. They have told it SCRs, right? So the active switches, that is S1 and S2 in this case, right? So in this case, S1 and S2 are given as SCRs. Okay. So how would the diodes be connected? The diodes will be connected in an anti-parallel fashion, right? So something similar to your MOSFET. Okay. So that is why the circuit diagram is something like this, correct? So you have your SCRs, that is T1 and T2, as you may call it. Okay. And you have the anti-parallel diodes. Okay, same circuit, just I have replaced this one and S2 with the CRs and the diodes. So the question is, find the conduction time of the diodes if the CRs are fired at 0 and T by 2 respectively in a single phase average inverter with R load. Okay, so what would be the waveforms if the SCRs are fired at 0 and T by 2? It would be same, right? So the SCR one SCR is turned on, or the T1 gets turned on at 0 degree, and T2 is turned on at T by 2 degree. As you can understand, your both of the ACRs are on for exactly the same duration, right? And they are on for entirely T by 2 cycle. Okay. So there is no question of freewheeling over here, right? So when does the diode come into play? The diode will come into play only if there's a freewheeling interval, right? So the inductor will force the current through the anti-parallel diode. But over here, it's given that it's a pure resistive load, right? In the question itself, it's given that it's a pure resistive load, R load. So there is no role of the diodes over here. Therefore, the conduction time of the diode is 0. Okay, so that's the question, right? So find the conduction time of the diode. Okay, so the conduction time is 0. So to A, right? Our answer is A. Okay, we'll move on to the next one. Right, for resistive load, the diodes will not conduct at all. The single phase average inverter has a resistive load of R equal to 2.4 ohm. DC input voltage is 48 volt. Find the value of the average supply current. So same topology, single phase average inverter, and it's only having an R load, it is 2.4 ohms. Okay. DC input voltage is 48 volts. Okay. So R is given, VDC or VS is given. Find the value of the average supply current or the source current. Okay. So again, draw the circuit and draw the waveforms. It will simplify things a lot. So you draw the circuit. Okay. Same single phase average inverter with R load and draw the waveforms. Okay. From here, you can try to analyze what happens. Okay. So your IA naught, right? Or the I naught is as given over here, right? It exactly follows your square wave, correct? Because it's a simple R load. So voltage is directly proportional to current. Okay. Now, the question is, what will be your source current? Correct? So that's the question, right? So what is your source current magnitude? So how do you find this out? So you try to analyze what will be the source current when, right? So when S1 is on, so you try to understand the path of the supply current, okay? So when S1 is on, what will happen? The current will flow something like this. If you can see my laser pointer, correct? So it will flow something like this. From the plus terminal, it will come something like this. Okay. And when S2 is on, it will come something like this, right? Okay, from O to A. Okay, so that is the path of your current. So now you can just need to sum it up and you will get the total current, right? Okay. So this is by waveform. Okay, by waveform, you can of course understand it. But theoretically, they have asked what is your average value of the supply current. Assume that the converter is operating at 100% efficiency. Okay, since nothing is given. So your input power should be equal to the output power, right? So the converter is just like a transformer, right? So whatever you give, it will either step up or step down the voltage or the current and just give you the output. It will convert to DC or AC, whatever, but the power remains the same. Okay. So in this case, you know what is your R and you know what is your input voltage as well, right? So try to use the power balance equation and get the output. Okay. So you can find out what is the output voltage from here, right? So VDC is given and R is given. So you can always find out what is your output voltage. So output voltage by current, by the resistance equals your output current. Okay. So output voltage into output current is your output power. Okay. And the output power is equal to your input power. So input power is simply input voltage times input current. So you can find out your supply current. So that's what I have done over here as well, right? So P is simply VA naught into I naught. Okay, VA naught into I naught. That's your output power. So what is VA naught? VA naught, as we can see, is VDC by 2, right? So VA naught is simply VDC by 2. Okay. And what is I naught? I naught is simply VA naught by R, right? So VDC by 2 over R. So VDC is simply 48 volts. So 48 by 2 is 24 into VDC by 2 by R. So 24 by 2.4. 2.4 is the resistance that's given, right? So it should give you your power. That is your output power, right? 240 watts. Since nothing is given about the efficiency, your input power equal to output power, right? So IS or the supply current is simply P divided by VDC. Okay. So 240 divided by 48. Okay, VDC is 48. Therefore, your IS or the input current is 5 amperes. Okay, it's simply power balance equation. Output power is V naught into I naught. So you know what is VA naught in a single phase average inverter, that is VDC by 2. And I naught is for a resistive load, I naught is VDC by 2 over R. So find out what is the output power. So output power divided by your input voltage gives your input current. Okay, it's a pretty simple question. Okay, fine. What will be the shape of the output current waveform of a single phase full bridge inverter on RL load? So observe the question. It is a single phase full bridge inverter and it's an RL load, right? Okay. So you might have, okay, first let us see the waveforms. So you can understand, right? So in a single phase full bridge inverter, how would it look like? I actually draw it. So you have this. So you have your two switches over here, and then you have the load, and then you have again two switches over here, correct? So what you do is you switch the devices in a complementary fashion, S1, S2, S3, and S4, right? So what you do basically is you will switch S1 and S2 together, right? S1, S2 together, and then S3, S4 together. Correct? So S1 and S2 will be from 0 to T by 2 and S3, S4 will be from T by 2 to T. So conventionally, this is what we do, right? So for half the time period opposite devices will be conducting, and for the other half of the time period, the other two opposite devices will be conducting. Okay. Now, what we understand is, what we understand is if I have an R load, right? If I have an R load, then the current is exactly going to follow my voltage. Okay. So let me name this as, point VA and this is point VO, or let me name this as VB. Okay. So how would my VAB look like? My VAB would look something like this, correct? So this is my VAB, right? So this is VDC and this is minus VDC. Pardon me for the handwriting. So actually my pen is having some issue. So I am using my hand to write on the screen. Okay. So your VAB is switching between VDC and minus VDC, depending on S1, S2 is on or S3, S4 is on. Okay. So this is for T by 2 and this is T. Okay. Okay. So you can understand if this load is a pure R load, right? If the load is a pure R load, then your um, then your output current will exactly follow VAB, right? Output current will be directly proportional to VAB and it will be a square wave, right? If it is a pure R load. But the question is for RL load. Okay, so generally for RL loads, what we may have is basically motors. Okay, so these are used in motor drive applications. Okay, so motor drives can be approximated as an RLE load, wherein your E is the back EMF, right? L is the armature windings inductance, and R is your armature resistance. Okay, generally your armature resistance is expected to be as small as possible to minimize your armature copper losses, right? So it will be an RL load dominated mostly by L. Okay, that's an example of an RL load. Okay. So the question is, what will be the shape of the output current if it's an RL load? So you can understand if it is purely resistive, it is going to be I naught will be exactly following your VDC, right? It will be something like this. Okay. So this is for a resistive load, right? And then if it was purely inductive, how would it be if it was purely inductive? So for this case, you just need to follow one simple thing. So you know that this is your VAB, right? So this is your VAB, right? This is your plus VDC. This is your minus VDC. Okay. So if the load is purely inductive, right? So what will be the current? Okay. So for an inductor, what do we know? Basically, just we know that V is L into di by dt. Okay. So what will be I? I is basically 1 by L integral VDT, right? So it is basically the current waveform. How will the current look like? The current will basically an integration of the square wave. Okay, if you integrate the square wave, you will be getting your current I naught. Got it? So how would it look like? So integration of a square wave, or you can do it piecewise also from 0 to T by 2. Just hang on for a second. I will just connect my laptop charger. Yeah, thanks for hanging by. Actually, my laptop just went out of charge. Okay. So as I was telling, if you have a square wave as the voltage across your load, and if the load is an inductor, right? So basically just follow V is L times dA by dt, right? Therefore your I or the inductor current is going to be 1 by L times integral V dt. Okay, so basically if you integrate this VAB, if you integrate this square wave, you are going to get your inductor current. Okay, simple, right? So if you don't know what's the integration of a square wave, you don't need to worry too much, right? So you just cut it piecewise. So over here, what is your VAB? VAB is a constant plus VDC, right? So between 0 to T by 2, between 0 to T by 2, your VAB is simply constant plus VDC, correct? So what is the integration of a constant? The integration of a constant is a ramp, correct? So if you integrate K, what is the integral k dt? K into time, right? If you integrate time. So it is just with time, it will go on increasing. K is just constant. Okay, it will just go on increasing. So what you will see in steady state, since this is an AC, is that you will see something like this, just a ramp. It will go on increasing. Okay. So what will be the value? Negative value and the positive value. Where will it start from? Basically, it is 1 by L times integral V dt, right? So it will be 1 by L into integral V dt. So what is its value? It will be minus VDC. It will start from minus VDC and it will go to plus VDC. Okay. So similarly over here, the from T by 2 to T, what will happen? The inductor current will fall, right? Why? Because between T by 2 to T, your VAB is minus VDC. So integration of a negative K is simply minus KT, right? So minus K into T. As the time increases, it will go more and more negative. Okay. So this is what you are expected to see. So when you have a square wave voltage across an inductor, what you expect to see is actually a ramp or a triangular wave. Okay. So this is what you expect to see in steady state. So the point is, they have told for purely resistive, we know it will follow VAB. If it was purely inductive, it will be a triangular wave or a ramp, right? And for an RL load, how will it look like? For an RL load, it is supposed to look somewhere in between a square wave, but not exactly a triangular, correct? So theoretically speaking, this is how it will look like, right? For purely inductive case, it would look like a ramp. Okay, as shown over here, it will look like a ramp or a triangular wave. Okay, and if it was an RL, it will look something in between. Okay, it will have a curvy nature, right? You would have studied about RL charging circuits, right? RL circuits, so wherein the charging and discharging is governed by 1 minus e per minus t by tau, where tau is your RL time constant. Okay, if your time constant is very large, that means your L is dominating too much. Okay, if your L dominates too much, then in that case, you can assume that this kind of exponential charging and discharging curve is almost like a straight line. Okay, almost like a triangular wave, right? If your L is very large, I'll just write it down. So if your L is very large, you can assume that it will be something like this. Okay, if your L is very large. So this is almost a triangular wave, right? So that is the question. How is the output current? Your output current looks like a triangular wave. Okay. So this is the answer. Okay, fine. Okay. Okay, so we have seen enough questions on single phase half bridge and just a question on single phase full bridge. Okay. In the three-phase bridge inverter, each step consists of dash 30, 60, 90 will depend on the value of the firing angle. So in a three-phase full bridge inverter, okay, as I told, just try to draw the waveforms in the converter. It will make life simpler for you. Okay. Yeah. So this is your three-phase VSI, right? So you have 6 switches totally. That is S1, S3, S5 on the top rail. Okay. And S4, S6, and S2 on the bottom rail. Okay. Specifically, this order has been written for simplicity. Okay, so that you know in what order the switches are being turned on: S1, S3, S5, and S4, S6, and S2. Okay, and what will be the waveform? The waveform is something like this, correct? So initially S1 will be on, correct? 0 to, that is from 0 to 60 degree. And then at 60 degree, the first switching will happen, right? Then 60 to 120, you have another state. 120 to 180, you have another state. Then similarly, something like that, right? 120 to 180, 180 to 240, 240 to 300, then 300 to 360 finally. Okay, this is how you switch the devices. Okay. And of course, you understand that individually in a half bridge, you cannot turn on devices simultaneously, correct? Because if you do that, it's going to be a dead short circuit, right? So you cannot turn on S1, S4 simultaneously, or S3, S6, or S5, S2 simultaneously. But you can, of course, have an overlap in the top rail switches or the bottom rail switches, and that's what we'll be having. Okay. At any point of time, if you see, right? One, two switches of the top leg and one switch on the bottom leg, or two switches of the bottom leg and one switch on the top leg will be conducting. Okay, so that's the idea behind the switching. Okay, and the switches will of course be, each switch will, if it conducts for 180 degrees, right? So S1 for 0 to 180 and S4 for 180 to 360. Then in the next leg, the switching is shifted by 120 degrees, right? At 120 degree, S3 will start conducting. Okay. At 240 degrees or minus 120 degrees, S5 will start conducting. So that's the idea. S1 is at 0, S3 at 120, and S5 at 240. Okay, and S4, S6, S2 will be complementary. Correct? So if you do that, and if you plot what is VA naught, VB naught, and VC naught, you can always get what is your phase voltage, right? And I mean, you have got your pole voltage. You can always get what's your line voltage, right? So what's VAB, what's VBC? Okay. So you know what is VA naught, and we will know what is VB naught. VB naught will just be phase shifted version of VA naught by 120 degrees. Okay. So just subtract them, you will get what is VAB. Okay, so that is the idea. So now coming back to the question is each step consists of what, right? So each step consists of obviously 60 degrees, right? So you are seeing over here VA naught, it remains at 1 by 3 VD, I mean, yeah, it remains at 2 by 1 by 3 VDC for 0 to 60. Then from 60 to 120, it goes to double of that value. And then again 60 to 120 to 180, right? So it's something like kind of a switch waveform, assuming that it's 180-degree conduction mode. Okay. So the step is basically 60 degrees. So the option is B. Yeah. Each step consists of 60 degrees. It is evident from the pole voltage waveforms itself, right? Just follow the simple logic that S1, S3, S5 are the three phases in a full bridge. Each of the switchings are phase shifted by 120 degree, right? S3 turns on after 120, S5 turns on after 240. So S4, S6, S2 are exact complementary of each other, right? So from this, you can always get what's your pole voltage, VA naught, VB naught, VC naught. And subtracting any of the two, you will get the line voltage, that is VAB or VBC or VCA. Okay, correct. So load phase voltage has 6 steps in one cycle. Okay, so coming back to the same question. In 180-degree mode VSI, how many devices conduct at a time? Okay, again, it's for the same question, right? So you just, you know the answer, I guess, by now. Just draw the waveforms and draw the topology. Simple. Okay, so you have drawn the waveform converter over here. Draw the waveforms as well. Okay, so S1, S3, S5 you have over here, and then your VAB as well, and VA naught as, of course, you know. The question is how many devices conduct at a time? Okay, you can see any particular segment. Okay, let's say at this segment. Okay, segment number 3, I guess, right? So S1 is on, S3 is on, and S2 will be on. So at any point of time, if you see in this 180-degree conduction mode, 3 devices are going to be on, right? So in the first, it's going to be S6, S1, S6, and then S5. Then S1, S6, S2. Correct? 60 to 120. Then 120 to 180, S1, S3, S2. Then 180 to 240, S4, S3, S2. Then 240 to 300, S4, S3, S5. Right? And then 300 to 360, S4, S6, and then S5. Okay. So at any particular point of time, any point of time in your entire line cycle of 360 degrees or 2 pi, right? Three devices will be on. Okay. In this 180-degree conduction mode. And what are the three devices? The three devices can be split as two devices in the top leg and one devices in any of the one device in any of the bottom leg, or two devices in the bottom leg, or and one device in the top leg. It can be either of that. Okay, it can be in any combination. Also, you observe that as you change from one state to the next state, for example, S1, S6, S5, then you change it out to S1, S6, and S2, right? So there is a change only in VCN, that is S5 becomes S2, right? Similarly, in the next S1, S3, S2, now there is a change in VBN. Okay, next will be S4, S3, S2. Now there is a change in VAN only. So you will see that as you progress from one state to the next state, right? There is a change only in one switch. There will not be change in multiple switches. So if you change from, let's say, 60-degree to 120-degree, then you go to 120 to 180-degree area, you will see that there is a change only in one switch. Multiple switches will not change at the same time. Each state, the transition from one state to the next state will be only one number. Okay. This is similar to something you might have studied in digital logic circuits, right? So you have only one bit change at a time. So those stuff you apply over there. Correct. So it's something like that. Okay. So there will be only one switch that's switching from one state to the next state transition. So, but anyway, to answer this question, how many devices conduct at a time? Obviously, three devices conduct at a time. Okay. Okay. So a three-phase bridge inverter delivers power to a resistive load, okay, from a 450-volt DC source. So your DC VDC is given and it's a three-phase bridge inverter. For a star connected load, observe the connection as well. Star connection or delta connection, it's quite important. And the options will contain answers corresponding to both star as well as delta. Okay, so for a star connected load of 10 ohm per phase, okay, determine the load power. So they have given you R, they have given you what is VDC, and you know it's a star connected load, okay, and it is also given its 120-degree mode of operation. Okay, so all your formulae should be rotated back to 120 degrees. Okay, don't think about 180 degrees and solve it. Even that particular answer will be given 180 degrees. Okay, so please be sure while solving. Okay, so your R is given, VDC is given, and it's a 120-degree mode, star connected, right? So it's a straightforward operation. So your load power is simply what? Load power is 3 times your phase power, right? So if you calculate what's the individual power in one phase, you multiply by 3, it's your total power. Yeah. So in your 120, just draw the circuit, and what happens in your 120-degree conduction? Obviously, it is not going to be 180 degrees, right? So each switch will conduct only for 120 degree, hence the name, right? So that's why it's called 120-degree conduction. Okay, so you have your S1 that is on from 0 to 120 degrees. Okay, 0 to 120 degree. Then 120 to 180 you have a dead time, right? It's called a dead time or non-conduction period. So wherein nothing, S1 and both S1 and S4 are off, simply off, right? Between 120 to 180. Okay. And from 180 to again till 300 degrees, right? That is again for 120 degree, S4 is on. Okay. And then from 300 to 360, again, it is everything is off. Okay, so you have 120 degrees of S1, 60 degrees of nothing, then 120 degrees of S4, again 60 degrees of nothing. So it's effectively 120 degree for each switch, and the remaining 120 degrees is a dead time. Okay, none of the devices are going to conduct. Okay, again, the subsequent legs are phase shifted by 120 degrees. Therefore, S3 will turn on at 120. So 120 to 240, right? And then 240 to 300 dead time. Then again from 300, it will start to the next cycle again till 120 degrees. So that's going to be your S6. Similarly, S5 will turn on at 240. So 240 to 360 S5. Then 0 to 120 is dead time. Then S2 is from 120 to 240 once again. Okay, so that's what has been drawn over here. Okay. So now with this knowledge, you can always draw what's your VA naught, VB naught, VC naught. Okay. So it's just going to alternate between VDC by 2, 0 to minus VDC by 2. It will only have two levels. I mean, it will only have single level. Okay. It's either plus VDC by 2 or minus VDC by 2. It will not have multiple steps like we saw earlier. It will not be going to 2 VDC by 3 and stuff. That particular phenomenon was arising only because three devices were on at a time. Okay. Over here, only two devices are going to be on, right? So from 0 to 60, you know that from 0 to 60 only S1 and S6 are on, right? And then 60 to 120 S1 and S2, right? 120 to 180 S3 and S2, then 180 to 240 S4 S3, 240 to 300 you have your S4 S5, and finally from 300 to 360 you have your S6 and S5, right? So only two devices are on at a time. So based on that, it's pretty simple. You can just find out what's your VA naught, and from this you can always determine your line to line voltage. Okay. But what we require is only VA naught for calculating the phase current. Correct? I mean the phase power. So you know what is your VA naught? You can always find what's your IA, right? IA is going to be simply VA naught by R. It's a pure resistive load, right? So you have your VA naught. So what will be your IA naught RMS? So mind you that since we have seen this previously as well, correct? So since it's a resistor, you always use your RMS quantity, not your average value. Of course, your average value is going to be zero over here, right? You understand that. Okay. So your VA naught, as you can see over here, VA naught, as you can see over here, it is a square wave, right? It's a quasi square wave. Why? Because it is VDC by 2 from 0 to 120, and it is 0 from 120 to 180. Then again 180 to 240, 180 to 300, it is minus VDC by 2, and then it is 0 from 300 to 360. So it's a quasi square wave with two-thirds of the period, right? From 0 to 120 and your to 180 to 300, you have a particular value, and the rest 120 degree, it's nothing, right? So the total on time is effectively 240 degrees on 360 degrees. Okay. Therefore, your RMS value. So what is your RMS value? If I have to write, correct. So your RMS is basically root over 1 by T, right? Root over 1 by T integral 0 to T f square dt, or that is a function square dt. This is a basic definition of RMS, correct? So what I will write is the RMS is over here, since it's a square wave, it is basically the amplitude, V amplitude, okay, V amplitude multiplied by root over T on by T. Okay. So what is your amplitude over here? Amplitude is VDC by 2. Okay, so VDC by 2 into root over T on. What is T on? It is either plus VDC by 2 or minus VDC by 2, totally for 240 degrees. 240 out of 360. Okay, so it might be better if I actually write it in a new slide. Um, okay, so what is going to be your RMS then in that case? your RMS is going to be VDC by 2 and then root over 2 by 3. Correct? So it is going to be something like VDC over root 6. Right? So this is your RMS value of your VA naught or your pole voltage. Correct? It is simply V amplitude multiplied by root over T on by T. Okay, so V amplitude is VDC by 2 into 2 to T on by T, right? So it's 240 T for 120, it's plus VDC by 2. For another 120, it's minus VDC by 2. So root of 240 or 360. Okay, so VDC by root 6. So now that you have got this, what you can do is power. What is power? Power is basically 3 times for 3 phases into V RMS square over R. V square by R, right? Into 3 for number of phases, 3 phases, 3 phase system. So you can always find out your power something like this. Okay. So this is what has been explained over here as well. They have done, I mean, I have done with using the current, but a simpler way would be something like this, 3V square over R, or you can also use 3I square R. Okay. So you should be ending up with the same answer in both cases. Okay. Okay, so let me solve it something like this. So 3 into VDC square, right? So VDC square over 6 into R. Okay, so 3 into so 3 and 6 are cancelled. So it is basically VDC square over 2R. Correct? So what is VDC? VDC is 450 volts, right? And R is 10. So it is basically 450 square over 2 into 10. Okay, if you do this, how much are we ending up with? Please, guys, it's better if you calculate. Okay, so 450 into 450 divided by 20. So it turns out to be 10.125 kilowatt. Okay, yeah, so 10.13 kilowatt. I'm going to pause over here and ask you if this was fine. I just found out the RMS value, then I did 3V square over R. Or you can also do 3I square R, it's your wish. But was this question fine? Can anyone please confirm if this was fine?
Yes, sir.
Okay. So I just do the waveforms. From the waveforms, it's quite clear, right? So RMS value is basically for a square quasi square wave, amplitude times root of T on by T. Okay. So what I did was basically for this square wave, amplitude V amplitude times root over T on by T. It is the RMS. If I know RMS, P is basically 3 V RMS square over R. Okay, simple, right? So T on is 240 degrees. T on is 240 and 3 is of course 360. Okay. What is V amplitude? V amplitude is VDC over 2. So VDC into root over 240 by 360. Okay, simple, right? So 3V square over R you do, you get the answer. Okay, or you can also use the current. Okay, because it's a quasi square wave and it's also a purely resistive load. The current profile will exactly follow this profile, right? So IA will be exactly something like this. So for the same thing, just find out the RMS value, and that's what has been done over here. I found the RMS and applied 3A square R, you get the same answer. Okay. Okay. The three-phase inverter has a star connected or a Y connected load of R equal to 5 ohms and L is 23 millihenries. Okay. So R is given, L is given. So it's no longer an R load. So current is no longer going to follow your output voltage. The inverter frequency is F is equal to 60 hertz. Okay, so for your information, 60 hertz is preferred in US. Okay, in Commonwealth countries we use 50 hertz, but in some countries we of course use 60 hertz. And the DC input voltage is 220 volts. Okay, determine the RMS line voltage. So DC input voltage VDC is given, F is given, and then your R is given, L is given. Determine the RMS line voltage. Okay. So determining the RMS line voltage, none of this is required, right? So just your VS is required and that's it. Okay, determine your RMS line voltage. If the question was determine the fundamental value of RMS line voltage, then yeah, probably fundamental value of the line current or something, then you need to know all of this stuff, right? But since it is only about the voltage, you need not consider this right now. Okay. So what is your RMS line voltage? It is basically the same, right? The same as what I did earlier. Okay. So you have your waveforms, correct? So it is simply the same. Okay. So this is for since they have not given what kind of conduction this is. Okay. What conduction this is, either it's 120 or 180, right? They have not given, right? Whether it's 180 or 120. So it is actually your prerogative to do both and find out which is correct. Okay, among the options. They have not given 180 or 120. Okay, so it is actually your duty to do both and find out where the answer is actually matching among the given options. Okay, only one among them will most probably match. If they don't specify anything and none of the options matches, then it's probably 180 degrees. People generally prefer 180 degrees, but over here the question is about 120 degrees. Okay. Anyway, we saw that the line to line voltage, correct? Or I'm sorry, the pole voltage in the case of 120-degree conduction is something like this. Correct? So, pardon me for this. Right, so you have something like, okay, so you have something like this, and then this is your 0, this is your 120, 180, 300, and then 360. So you are seeing that it is on, right? So you have a plus VDC by 2 and a minus VDC by 2 for 120 degrees. I'm 120 degree over here and 120 degree over here. So total of 240 degrees, right? So simply it is V amplitude into root over T on by T. That is your RMS, correct? So what's your amplitude? It is 220 into root over T on by T, right? So 240 over 360. Okay. So it is simply going to be 220 into root over 2 by 3. 220 into root over 2 by 3. Okay. So that's what we have done over here as well. That is, it turns out to be around 180 volts, 179.629. 7, yeah. 179 B. Okay, it's the same thing, right?
So yes,
Okay.
sir. So is it for 180 degrees and how to calculate, sir, RMS?
Same thing. You just need to draw your, if I go back to the waveforms. Yeah. So this is for 180 degrees, correct? Um, in the case of VAB, right, it's your line to line voltage, the RMS will be same, right? It's simply going to be T on by T, right? So amplitude VDC into root over T on by T. It is your, in the case of line voltage. Okay. This is your line voltage. So for the line voltage RMS, you know what is your RMS, correct? In the case of line voltage, you can always find out the RMS of this waveform VA naught. Okay, but you can see that it's quite tedious, right? Like you have some voltage over here, you have some other value over here, then again something over here, right? It is again different over here, different over here, and different over here. Okay, so there are two ways of going about it. One is if you just draw this, you're just going to go on calculating the RMS before you even touch the problem. Okay, simply you know that this is going to be V amplitude into root over 2 by 3, right? Root over 240 by 360 or root over 2 by 3. Okay, this is the line. If this is the line, let me take a new slide over here. Okay, so I know that line is going to be simply V amplitude into root over 2 by 3. So can you tell me if the line is something like this, what will be the V phase? What's the relation between line and phase voltage? If it is star connected, of course.
Root 3, sir. Root 3. Line
Correct.
voltage. Yes, sir.
So line by root 3. So VA root over 2 by 3 divided by root 3. It's going to be VA into root over 2 over 3. Okay. This is the simplest method. Please follow this method. Follow this. The other method is you don't even care about the line voltage and just you draw this. Okay. You will go on doing this because the procedure to solve this kind of a waveform is something like you split the waveform. Okay. Do this individually, correct? And then do this individually. And then by superposition theorem, you need to add it up. Okay. You will eventually get this expression, but you know that it's going to take a hell lot of time, right? Just remember that uh, you have a waveform something like this in the line. So you can easily find out the phase. It's a very good question. Thanks for
Thank you, sir.
asking this.
Thank you,
Okay,
sir.
it's a very good. I think if I remember correct, so questions I have seen some questions like this appearing in GATE or some competitive exams. Okay, they will precisely as you told, they will be asking the RMS value of the pole voltage. Okay, and students get stuck because they know the waveform, but they don't know the exact RMS value. If of course some people mark up, then it's a different issue. But simpler way is if you know the waveform, right? You know the waveform that it's going to be something like this. If the waveform of the line is this, the phase is simply by root 3, right? And if you need to find out the power and all, or if suppose they ask you the phase current, IA is simply what if it's an R load? VA naught over R, correct? Over here. So to find out IA RMS, so VA not RMS over R, correct? So now to find out VA not RMS, it is simply V line RMS over root 3 divided by R. Simple, right? So you just follow this. Or if you can just have it as a rule of thumb that in your 180-degree case, the line is equal to the phase of 120-degree. Okay. The phase of your 120-degree is equal to line of your 180. Let me write. Phase of one 180 degrees, right? Phase of your 180 degrees is equal to line of your, oh sorry, I'm writing in the opposite way, correct? Your phase of 120 degree is equal to line of 180. Okay, I mean not equal to exactly, it is wave shape, just the wave shape. Okay, because of course you understand that it's VTC by 2. Okay, so just the wave shape, if you see, it's a quasi square wave, right? So just you can just have these things in mind, so it will be easier for you. Okay, just use your this thing a little intelligence. You will be able to solve it. Good question. Right. Now over there also vice versa you can tell, right? So over here you told that the line voltage is simply using this. You can find out V amplitude or VDC into root over 2 by 3. Therefore, the phase is going to be divided by root 3. Over here as well, you can find out the same thing is applicable, correct? In a 120-degree conduction also. So in 120-degree conduction, uh, you knew that this is your pole voltage or the phase voltage. So what will be the line? Line is simply phase into root 3. Correct? Correct. So it's going to be VDC by 2 into root over 2 by 3. It is your phase voltage RMS. Into root 3 you multiply, you will get your line. Okay, what will be it? 3 and 3 are going to get cancelled. So root 2 by 2, right? So it's going to be VDC by root 2. This is your line RMS. Got it? Vice versa is also applicable. So whoever asked the question, can you please reply if this is fine?
Yes, sir. Fine, sir.
Okay. Yeah, it's a good question and it's a good hack as well. Just know the RMS of one, you will know the RMS of the other. And same applies for both 180 and 120 also. Thankfully, in 180 and 120, you have this one of them having a quasi square wave. But just be aware of the amplitude. Here it is VDC by 2. Okay. And over here, if I remember right, it was just VDC. Yeah, it is just VDC in 120-degree case. I mean, in 180-degree case. In 120-degree, it was VDC by 2. Okay, so take care of that stuff. Just I was telling in terms of the wave shape. Okay, so far so good. We will go to the next question. In sinusoidal pulse width modulation, the comparator output is high when dash. Triangular wave has magnitude higher than the sine wave. Sine wave has magnitude higher than triangular wave. Triangular wave has magnitude equal to sine wave. None of the above. Okay. So generally, both of them are fine. Like both of them can be both of A and B can be used for generating the PWM pulses. As a convention, we take option B. Okay. That is when sine wave goes more than triangular wave, then the comparator output goes high. We have a comparator, something like this. Okay. So you will be feeding V sine over here and V reference of the V triangular over here. When V sine goes more than V ref, it will be plus VCC or else it will be minus VCC. It's just a convention, okay, but both of them are applicable. Okay, you understand that both of them are applicable. Okay, both of them can be used, but logic 2 is generally used. It is because this is just a reference, correct? So you tell that something is set when your wave goes more than the reference wave. So reference is triangular. Okay, so your wave is sinusoidal. That's what you want. Sine is what you wanted the output sinusoidal wave. Therefore, when sine wave actually goes more than triangular wave, you want to set it. So that's a convention. Okay. Several equidistant pulses per half cycle are used in dash type of modulation technique. So from the question itself, it is evident. So several equidistant pulses, right? So it is used in multi-pulse modulation. Multi-pulses per half cycle are used in, several equidistant pulses per half cycle are used in multi-pulse type of modulation technique. Okay. Okay. So next question is again simple. This is something you might have studied in your week 2 as well. The distortion factor. What is new? The distortion factor. Total RMS output voltage to fundamental RMS output. Fundamental RMS output voltage to fundamental average output voltage. Total RMS output voltage to RMS value of all harmonic components. fundamental RMS output voltage to total RMS output voltage. So I guess you should be able to tell this by now. It is basically V fundamental or VO1. Okay, 1 is N, okay, divided by VO total. So that is option D. That is fundamental RMS. Of course, this is RMS. So VO1 divided by VO RMS. The fundamental divided by total. That's the idea. Okay, so that's the distortion factor. Of course, you can find out what is the distortion factor for single phase, three phase, right? For different kinds of PWM techniques as well. You will see that for three phase, generally three phase distortion factor will be more than your single phase case, right? Okay, so far, is there any doubt? I'll just
No,
have.
no, sir.
Okay, okay, thanks. Just pause for 2 minutes. I'll just have some water. So, yeah, thanks for that. Hmm. So we'll go ahead with the next question. One question I saw in the chat box was no dead time between S1, S3, and S5. So actually there is dead time means there is a phase shift of 120 degrees between S1, S3, and S5. Okay, always. So S1 turns on at 0, then S3 turns on at 120 degrees. Okay, so S1 turns on at 0, S3 at 120, and S5 at 240. Okay, and similarly, this is quite complementary. So it will S4 will turn on at 180, and this is 120 plus 180, right? 300, and this is 240 plus 180. So what's so it's basically minus 120 minus 180. Okay, so it will be minus 300. Yeah. So there is a difference of 120 degrees. Fine. Okay, so we'll go ahead with the next question. A single phase half bridge inverter is connected to a 230-volt DC source, which is feeding an R load of 10 ohms. So again, see, it's a single phase half bridge inverter and the DC source is given and R load is also given. Find the average current through each SCR switch, right? So again, it's a pretty simple problem, but it will be better if you draw the circuit and the waveform so you'll be able to understand. Find the current through each ECR switch. Okay. So you understand when the devices will actually be conducting. Okay. So when S1 is turned on, so there is going to be a positive voltage over here between 0 to T by 2. And when S2 is turned on from T by 2 to T, there is going to be negative voltage across VA0. So just draw the waveforms. Okay. So VA0 is something like a square wave, something like this between VDC by 2 to minus VDC by 2. Okay. So S1 was on from 0 to T by 2. So S1 was on 0 to T by 2 and S2 was on from T by 2 to T. Okay. So what is the current of S1? S1's current is going to be something like this, right? So it is I naught from 0 to T by 2 and it is 0 from T by 2 to T. Okay. Similarly, what is the current of S2? It is going to be something like this, correct? So it's going to be minus I naught from T by 2 to T and 0 from 0 to T by 2. Okay. So what is the average current? Average current is simply I naught into T on by T. Correct? So that's the average, right? So I naught into T on by T is what? T by 2 by T, right? So T by 2 by T, each switch is on for T by 2 period. So I naught by 2. That's the average current. Correct? So this is the I average. Okay. So this is the current of S1 and this is the current of S2. Okay, simple, right? Right. So just calculate what is I naught, do I naught by 2, you'll get the answer. Okay. So what is I naught? I naught is basically V naught by R. Okay. What is V naught? V naught is VDC by 2. Right. So VDC by 2 over R. So that is what I have done. So the current through each SCR is 11.5 amperes. Okay. Peak current. Okay. So the average, what will be the average current? Average current is simply, since each SCR conducts for 180 degrees, average current is simply 11.5 over 2. Okay. Simple, right? So this is the average current to each SCR, not the RMS current. It's the average current. Okay. If they had asked the RMS current, you need to do accordingly. Okay. So what will be the RMS value of this waveform? So if it was an RMS current question, so what's the RMS value of this waveform? Simply I naught into root over T on by T, right? So I naught over root 2, right? So I naught into, so the average was I naught by 2, correct? The RMS will be I naught by root 2, correct? I naught into root over T on by T. Understood? So can anyone tell me if this point is understood regarding the RMS current of the device? It is simply P current or the I naught current into root over T on by T. Okay.
Yes, sir.
Got it? Okay. So based on that, if they ask something like what's the power dissipated and all, it is simply I RMS square into R, power dissipated. Okay. So just have the distinction between RMS and average, so you'll be good. Okay. So what would be the harmonic factor of the lowest order harmonic in case of a half bridge inverter? Okay. So if your fundamental is 1, right? So that's the meaning of this question. On this side, you have your fundamental. If the fundamental is 1, what is the lowest order harmonic? Is it second order harmonic, third order harmonic, or this doesn't make much of a sense, but anyway, yeah. or insufficient data. What's it? Okay. So I guess all of you would know the answer that it's the third order harmonic, that's the lowest one. But anyway, so for a average inverter or for any square wave, right? So if you take any square wave, you know that it can be resolved into a number of sinusoidal components. This is the fundamental. And then you have your third, I'm sorry, this is the second order, correct? And then you have the third order, right? This is the third order, and then so on. So if you add up all of these components, you are going to end up with a square wave. That's the idea. So the question is, what is the lowest order harmonic? So you have your fundamental, What is the lowest order harmonic? N is equal to what? Summing up with, you will get this average, square wave. So the the output voltage by Fourier series, right? The even terms will cancel out. N is equal to even will cancel out. N is equal to even will cancel out. So only the odd terms will be remaining. So n equal to 135 to infinity 4 VDC by 2 by n pi sin n omega t. Okay, for any square wave, the components are sigma n equal to 1, 3, pi to infinity, or n is equal to odd to infinity 4 Vs by n pi, right? Where this is Vs. Okay, this is the square wave. For a square wave, this is the formula 4 Vs by n pi sin n omega t. So this is the amplitude. If you do by root 2, you will get the RMS. 4 Vs by n pi by root 2, if you do, it will be the RMS of that particular component. So now over here, right? So now over here, since your Vs is equal to VDC by 2, right? Why? In a half bridge inverter, it's VDC by 2, right? So this is VDC by 2, this VDC by 2, VDC by 2, VDC by 2. Therefore, 4 VDC by 2 by n pi sin n omega t, where n is 135. Therefore, lowest order harmonic is 3, right? So that's the answer. The answer is 1 by 3. Okay. But just this, remember, this is a thumb rule that for any square wave, it is 4 Vs by n pi. Okay, that is the peak. So by root 2, if you do, it is your RMS. Okay, and substitute Vs by the corresponding thing. It may be VDC or VDC by 2, whatever. Okay, we just substitute it properly for different kinds. If it's a full bridge, it's VDC. If it's a half bridge, it's VDC by 2. Okay. A single phase full bridge inverter using transistors and diodes is feeding an R load of 3 ohm and the DC input voltage of 60 volt. Find the fundamental frequency output power. See, read the question properly. Sorry to WhatsApp. Fundamental frequency output power. It's not just the average output power. It's a fundamental frequency. So you need to find out your V RMS fundamental into I RMS fundamental. Okay, for a single phase full bridge. Simple, right? So we just saw the associated problem previously. You have a square wave. How do you find out the fundamental, right? So that's something like that. A single phase full bridge inverter using transistors and diodes, okay, is feeding an R load with 3 ohms R. So R is given 3 ohms. VDC is 60 volts. Find the fundamental frequency output power. Okay, so how do you find this out? Just add a new slide over here. Yeah. So how do you find it out? As I have told earlier, just draw the equivalent circuit diagram. Okay, so the output voltage is going to be something like this, correct? Where this is your VDC for a full bridge, right? It's not a half bridge. If it was half bridge, it should be VDC by 2. It's going to be plus VDC to minus VDC, and it's going to be T by 2, T0. Okay. So as I told earlier, this can be resolved into its components, right? So the any square wave, right? It can be resolved as, so V naught or VAB in this case is going to be sigma n equal to odd to infinity 4 VDC by n pi sine n omega t plus phi. This is the formula. Okay, sine n omega t plus phi, where phi is tan inverse n omega L over R. Okay, simple. It's an RL circuit, right? So tan inverse n omega L over R, where n is the harmonic number. Okay, over here it's a pure R load. Therefore, phi is 0. Okay, you need not worry about it. So your voltage is given by sigma n equal to 1 to infinity 4 VDC by n pi sine n omega t. Okay, because your pi is 0. Why pi is 0? L is 0. There is no L. So since there is no L, it's a pure R load. How is your current looking like? Current will follow your voltage, correct? So the current will look something like this. Okay. So what is VAB RMS? VAB RMS is going to be 4 VDC by pi fundamental. Okay. 4 VDC by pi by root 2. That is your VDC RMS. And what is your IRMS? I1 RMS is going to be same V RMS, V1 RMS by R. Right? Simple, right? So, VAB RMS is equal to IAB RMS is equal to 4 VDC by pi by root 2 whole divided by R. Okay. So it is basically the power is basically what? This is the fundamental. Okay. Fundamental power. Fundamental power is basically VRIM1 into IR1. Okay. Into cos phi is there, but into cos phi, but phi is anyway your 0 and therefore cos phi is 1. Okay. So it will be, yeah, it will be V square or R. Okay. 16 PDC square over pi square into 2 divided by R. Okay, so you can do this. So how much is this? 60 and 3 moves, right? So 16 into 60 square divided by pi square into 2 over R. Yeah, so it's around 9.6 kilowatt if I'm right. Yeah, so correct. So it turns out around 972. Yeah, correct. Okay. Simple, right? Just apply the V square over R formula. Okay. And it is the fundamental value. So 4 VDC by n pi by root 2, that is your RMS. That square divided by R. Okay, R is given and the input voltage is also given. So it turns out around 972 watt. Okay. Okay. In multiple pulse modulation, the square wave is dash signal, whereas a triangular wave is a dash signal. So in any kind of modulation, you know that square wave is the reference signal, reference signal, triangle is a reference signal. I'm sorry. Sorry, it's not about the reference, it's about the carrier, right? Yeah, so it's either A or C, correct? So triangular wave is generally taken as the carrier signal. Okay, so triangular wave is the carrier signal and square wave is the reference signal. Okay, so square wave is the I marked it wrong. Square wave is the reference signal, triangle is the carrier signal. Correct. In single phase modulation of PWM inverters, the lowest harmonic can be eliminated if the pulse width is equal to dash. Okay, so I guess you have studied about this already, but yeah, there is a this thing that your pulse width, right? Your pulse width needs to be equal to 2 pi by n. Okay, pulse width we denote as 2d, right? That should be made equal to 2 pi by n. Okay, so that's the idea. So over here in single phase PWM, the lowest harmonic can be eliminated if the lowest harmonic is what we saw earlier itself, that n is equal to 3. This is the lowest harmonic. So how can it be eliminated? The pulse width needs to be made equal to 2 pi by n. Okay, that is 2 pi by 3, right? So what's 2 pi by 3? It's 120 degrees. Okay, so for eliminating the third order harmonic, the pulse width is made equal to 120 degrees. Okay, yeah. So option 3, 2 pi by 3. Okay. So the final question in this problem set, a three-phase bridge inverter delivers power to a resistive load from a 450 volt DC source. Okay, so DC source is given and a star connected load of 10 ohms per phase. Okay, R is 10. Determine the load power when the inverter operates in 180-degree mode. It's a common question, right? So I think you may be master of this by now. So VDC is given, right? Star connected 10 ohm is also given. Okay, so what is your output power P is 3 into V square by R or I square R. So whatever is your thing is V square per R. Okay, simply they have asked the output power. Just calculate your RMS and then you get the answer. Okay. So someone was asking previously also like how do we calculate, right? So sorry, we'll just do that once. So as we saw earlier itself, in a single phase, in a three-phase inverter, your line to line voltage, right? Your line to line voltage is given as something like this. Okay, this is your line to line voltage, where this is till 120, 180, 300, 360, right? And this is VDC and this is minus VDC. Okay, so this is your line to line voltage. So what is the RMS of this? The RMS of this voltage is going to be given by VDC into root over T on by T, right? So VDC into root over 240 over 360. That is VDC into root over 2 by 3. So this is the RMS of line, right? So this is the line RMS in 180-degree mode. Okay. So what's your phase RMS? Phase RMS is going to be line RMS over root 3. Okay. So VDC into root 2 whole divided by 3. This is your phase RMS. You got this. So power is simply 3 times phase RMS square over R. right? 3V square R, 3V square over R, right? So if you do this, you will end up with 13.5 kilowatt. Okay, everything is given, VDC is given, R is given. Just you apply, you will get it. So is this fine? Is this question? Can anyone tell me if this is fine, or else I'll be happy to repeat how this came about.
Fine, sir.
Everyone, Sudarshan, Anbuvan, um, Abhishek and Pavan, is this fine? Is this particular question?
Yes, sir.
Yeah, thank you. Okay, so I'll just tell this question once again. If you go to the waveforms, right? So waveform of your three phase, correct? Yeah. So this is your three phase VSI in 180-degree mode. So this is your line, right? So this is your line voltage, and this is your phase or pole voltage. So what you need to calculate the output power is basically 3 times the individual phase power, right? So you need the RMS of the phase voltage, but it is tedious to get the RMS of phase voltage. Instead, just find out the RMS of line, okay? And then you multiply by or you divide by √3, you get the phase RMS. So 3 into phase RMS square over R. Okay, so that's what we did. Okay, so we have seen such a question for 120 as well as 180 conduction mode. So it should be, I think, this much is enough for reference purposes. Okay, so far so good. So we have around half an hour time. We can see some extra problems. So just hang on a second. I will add some few slides. Okay. Okay. So just give me a 2-minute time. I'll just bring some water and take the questions in my hand. So this is your question number 18. Okay. So given that um, there is a full bridge inverter, Okay. So what is a full bridge inverter? It's a single phase full bridge inverter. Okay. It's a single phase full bridge inverter or a voltage source inverter operating at a frequency of 400 hertz. Okay. It's operating at a frequency of 400 hertz and it has a DC supply of 220 volts. Okay. Full bridge single phase VSI has a DC supply of 220 volts. Okay. Find the fundamental component of the output voltage. Fundamental component of output voltage. Okay. So simple, right? I think by now you'll be masters. So for a single phase full bridge inverter, the output voltage is something like this. Correct? So this is T by 2, T0. This is plus VDC and this is minus VDC, right? Single phase full bridge. It's not a half bridge. If it was half bridge, it will be by 2 by 2. Correct? So your RMS is given by N is equal to odd to infinity 4 times VDC by N pi sine N omega T plus phi. Okay. It is feeding an R load. Okay. So therefore phi is 0. So what is the fundamental RMS? RMS fundamental is 4 VDC by pi by root 2. Correct? So what is the answer? 4 into 220 by pi by root 2. So if anyone solves it, you can tell me the answer or I need to do it. 4 into 220 by 1.44. So it is around 198.1 volt. Okay. So it's a
Yes.
single phase. Yeah. Good. So VDC is also
Sir,
given. Yeah. Yeah, yeah.
so like in class in lecture slides, there was one
Hmm.
one topic like multi-level inverters and like
Hmm.
there the sorry is explaining like the reason why we go to multi-level in inverter is like we don't
Hmm.
make full utilization of DC voltage in single level inverter. Okay, so can you
Yes.
please explain that, sir? Like how we don't make use of full voltage level?
Yeah. So the point is, for example, if you take half bridge, you understand, right? Like you don't make the utilization of full this thing. Correct? In a half bridge inverter, you only get plus VDC by 2 to minus VDC by 2. That is one thing. Second thing is, even in a full bridge inverter, what is a see? For example, you tell that the average or the output power is supposed to be V naught into I naught. Okay. But the useful power is actually only the fundamental component. Okay. Rest of them is harmonics, which will just cause heat up, right? You don't want that. Correct? So if you see the harmonic, this thing, harmonic, effective harmonic thing after, your effective fundamental voltage after you neglect all the harmonics, you see over here, for example, for a VDC of 220 volts, the effective output voltage that you actually can use for your load is basically only around 198.1 volts. You're losing some 20 volts, right? Correct. So the idea is if you go towards multi-level converters, instead of seeing something like this, you are expected to see something like this. If I draw it, I am drawing very lesser number of steps, but so you see that it is almost like a sine wave, right? Correct. It is almost like a sine wave, correct?
So, yes, sir.
So what you will see is the RMS value will be really high. RMS of the fundamental will be really high. It will approach towards 220, maybe some 212 or 215 or whatever. Okay. So idea is there will be lesser losses. and whatever 220 volt you give, entire 220 volt is being utilized for getting your output power. Okay.
Yes,
So
sir.
that is why we go for multi-level converters, basically to reduce the harmonic content. If you reduce the harmonic content, obviously it's a better utilization, right? Because you're getting more RMS voltage. So if you get more RMS, basically you're getting more V square over R, correct?
Yes, sir.
So that's the reason. Okay, because you see over here, if you don't if you see just square wave, it is composed of a square wave is supposed to be composed of infinite number of harmonics. That is the definition of Fourier series, right? Fourier series goes from n equal to 1 to infinity. Okay, so basically you're defining the square wave as a summation of infinite number of sinusoidal components. That means infinite number of harmonics are there, which you don't want, or you want the percentage of fundamental to be really high. Okay, so that's the reason we go for multi-level converters. If you do the harmonic analysis of multi-level converters, you will see that it is much better for multi-level compared to this.
So can
Okay,
you explain, sir, jet source inverter, sir?
Z source inverter. Maybe I can do it in the next class. Right now, I don't have the material to explain directly. So this was supposed to be a problem solving session. So I didn't really find any problems on Z-source inverters, so therefore I didn't take that up. But yeah, maybe I can explain in the next class for sure.
So theories are only theory, like not
No,
problems.
I get it, I get it. So I also need to read, I mean, check it once, go through it once. So yeah, probably in the next class I will explain. No problem.
So in one of the lectures, it's mentioned the linear operating range of PWM is 0.707 or something, so that efficiency of output is lower. I did not exactly understand that point.
Sorry,
Could you
sorry, sorry.
explain?
I didn't hear you.
To operate the inverter in the linear range, the modulation index has to be less than 0.707. I think some sort of statement was given in one of the lectures.
Okay.
So what exactly is that? I mean, over modulation is mentioned, but how is this number 0.707 come up with around 0.7
mm,
for linear operating range?
and to be honest, I also need to go through the lectures once because since we are doing this problem solving sessions, we focus only on the problems. So, but anyway, I'll be happy to note them down and I can tell you in the next class probably all these queries.
Okay, sir. Thank you.
Okay. Just give me a second. Let me just note these down. Z source inverters, right? Okay, fine. I will just go through, look up these things and tell in the next class. Okay. Because you understand, right? We are focusing more and this is supposed to be problem solving session. So we just focus on the problems only. But anyway, it's not a problem. I will tell in the next class. Okay, so next question is. Yeah. This is a question on three-phase inverters. Okay, so the question is a three-phase inverter has a VDC of 300 volts. Okay, simple, right? And it is so there are two subcases to this question. Okay, so one thing is part one is find V phase RMS assuming 120-degree conduction mode. Okay, find V phase RMS and then find the output power P out. Okay. Next question is, this is for Y connection. Third and fourth are the same questions, assuming a delta connection. Okay. So just give me a second. Let me just solve this problem. You got the question right. You have a three-phase inverter. So you have a three-phase full bridge inverter. It's operating in the 120-degree mode with a VDC of 300 volts. Question is, find the V phase RMS and then find the output power. And this should be done for Y connection and delta connection of the load. Okay. So just hang on a second. Yeah. And the load resistance is actually 10 ohms. Okay. Load resistance is 10 ohms. So assume 120-degree conduction and solve. So what did we do in 120-degree conduction? You know that the phase is going to be something like a quasi square wave. Correct? Phase is going to be a quasi square wave. So what is your phase RMS? V phase RMS. V phase RMS is going to be VDC by 2 into root over 2 by 3. Correct? This is VDC by 2. If I'm right. Yeah, this is VDC by 2. Okay. So this is your V phase RMS simply, right? So what will be your yeah. So this is your V phase RMS. What is your V line RMS then? V phase RMS into root 3. Correct? So it is going to be VDC root 3 over 2 into root over 2 by 3. We can simplify this later. Or okay, VDC by root 2. This is your V line RMS. Okay. So this is in case of star connection. I'm sorry. This is in case of star connection. So what happens in case of delta connection? In case of delta connection, you will see that your V line RMS is equal to V phase RMS, right? So in delta connection, your V phase RMS and your line RMS are going to be same, which means that your V phase RMS is also going to be VDC over root 2. Okay, if you know this, you solve your problem is done. Got it? Question was for Y connection and delta connection. For delta connection, line and phase both are same. Okay. So just I know this one particular graph of your phase voltage in a 120-degree conduction mode. So I know what is my line voltage, correct? For Y connection. Then for delta connection also I know, right? Because if I know the line from star, it's going to be the same for delta also, right? So it's again going to be VDC over root 2. Okay. With this knowledge, you can go ahead and you solve the question. So what is V phase RMS? So V phase RMS is what? VDC by 2 into root over 2 by 3. Okay. That is 300 by 2 into root over 2 by 3. And you should get somewhere around 122.5 volts. Okay. And this is for star connection. P is what? 3 times V phase RMS square over R. Okay. Right. So 3 into 122.5 square over 10. Okay. So you can solve this and someone can maybe tell me the answer. And what is for delta connection? So this is for star, this is for delta. So for delta connection, V phase RMS is equal to V line RMS, right? Which is VDC over root 2. right? So 300 over root 2, which turns out to be 212.1 volt. Okay. So what will be your power then? Power is again same 3 V phase square over R. Okay. Or one hack is this power will be what? This power will be 3 times your power of star. Correct? Because your V phase and line are equal, right? And you are squaring it. Okay. So it will be 3 times the power whatever you get here. Got this question, all of you? Is this question fine for you guys? That is simple question. They have just asked, they have given you that DC value. Okay. 120-degree conduction mode. Okay. And they have given you your R also. Find the phase RMS of the phase output voltage. Find the output power. In case of star connection of the load, same load is connected in delta. Okay. With same R. Okay. Same load is connected in delta. Find the output voltage. Just be sure of your fundamentals. Okay, for 120-degree conduction, you know the waveform of your phase. This is the phase waveform. You know the waveform of your phase. It's a quasi-square wave, VDC by 2 to minus VDC by 2. Okay, just find out what is V phase RMS. Then you know what is V line RMS in star case because line is simply phase multiplied by root 3. In delta, you know that your line and phase are going to be same. Therefore, your phase voltage is VDC over root 2, whatever you get over here. Simple, right? So once you know this, then you know everything. That is phase you can find out P is simply 3V square by R, right? So do that for star, do that for delta and you're done. Okay, so did anyone solve this problem? What's the power that you get? 3 into 122.5 into 122.5 over 10. So you should get 4.5 kilowatt. Okay. And this will be 3 times of that value probably. So you will be getting 13.5 kilowatt. Right? Okay. So 3 V phase, yeah, 3 into, or you can also do this 3 into VDC square by 2 over R. Same, you will end up with the same answer. 3 into 3 into 300 by 2 by 10. Yeah, you will end up with the same answer. Okay, 13.5 kilowatt. Okay, so you also remember this thumb rule, right? So P in star and P in delta, how they are related, right? So if they give you one, you can easily find out the other. No need to go through any of this stuff. You know that P in delta is 3 times P in star. Okay. So you see that in this 120-degree mode, P delta is more than P star. So if you connect the load in delta mode, you are going to get more output power, right? And you also know that in 180-degree mode, the output power is more than 120-degree mode because switches are on for more time. So if let's say someone asks you, I have a three-phase inverter, I can configure it in either delta or star. I can run it as 180-degree or 120-degree. Okay. Question is, I can configure it as 120-degree or 180-degree. I can configure the load as delta or star. So if someone asks you in which mode will I get maximum output power, I want to get maximum output power. Then to get maximum output power in which mode will you run? You got the question? That is, I can run it in 120-degree mode or 180-degree mode. I can run it in delta or star. which will give you maximum output power, which will give you the least output power. If you see, the maximum output power will be obtained with 180 degree and delta, and minimum you will get with 120 degree and star. Okay, this is just after seeing all of these problems, we are able to comment something like this. Correct? If you do the math for all of these, you will see this being satisfied for the 4 cases, 120 degree and 180 degree conduction and delta or star connection. You will see that you can harness maximum power with this. Okay. Okay, so do we have time for one more probably? Yeah. Okay. So one more question. This is just a simple. 20th question. Let's conclude with this question. It's a small question. Okay. So to eliminate fifth order harmonic, fifth order harmonic, what should be the pulse width? We saw earlier, right? What should be the pulse width to eliminate the lowest order harmonic, that is n equal to 3. Now they are asking for n equal to 5. What should be the pulse width? So what should be the pulse width? Pulse width should be 2 pi over n is equal to the pulse width 2d. Okay. So that is 2 pi over 5. What is 2 pi over 5? 72 degrees. Okay. Fine. Even you will see that multiples of these will also eliminate. So 72 into 2. What is 72 into 2? 144. So this will also help in eliminating the fifth order harmonics. Okay, multiples will help. So 72 and 144 degrees. If you use as the pulse width, you can always eliminate your fifth order harmonic. 2 pi over n, that's the key. Okay, for 3, we saw that the pulse width should be 120 degrees. Got it? Okay, so I guess we are time. We can stop over here perhaps, yeah. And we can stop. Yeah, so we can stop over here perhaps. Okay, so we have seen around 20 problems. And of course, yeah, I will look up on these topics, that is a linear modulation index up to 0.707, and of course the Z source inverters, and we can have the last 10 or 15 minutes in the next class for that. Okay, for having that apart from solving the problems. Okay. So if you have any other doubts, please do let me know, or you want me to check anything, please do let me know. I'll be happy to do so. I'll just pause for a moment, or else we can conclude for the day. So Abhishek, Sudarshan, and Pavan, if you have anything, please do let me know now, or I will stop my sharing.
No, sir. Like it's okay, sir. From my side.
Okay. Okay, thanks, Sudarshan. Yeah, okay then. We will stop for the day. I will stop my recording. Stop.
Thank you.
Yeah, thanks, Abhishek.